In this lecture, we're going to talk about oxidation reduction reactions and a property called cell potential, how we can quantitate the potential for these oxidation reduction reactions. Okay, so let's consider a process called galvanization, where a zinc metal coating is put over steel, and this is used for things like fences, gutters, and roofing materials. So if we look at this, right, so let's consider we have zinc. If that steel begins to rust, we get some iron 3. But with the zinc present, the zinc reacts with the iron, and we'll write this as an equilibrium reaction, but it's going to move to the right so that you get your iron 3 reduced back to iron. It protects the iron from rusting, and the zinc becomes oxidized. Right? And let's leave ourselves a little more room here. Right? And if we balance this, it's 3 to 2. Right? And so this is an oxidation reduction process, right? Zinc is going from zinc metal to zinc ions, which means each zinc atom is losing 2 electrons, right? That is an oxidation, right? That's how we define oxidation. Something is losing electrons in the process. Iron 3 ions are going to back to iron metal, which means each of those has to accept 3 electrons, right? That is reduction. And just to remind ourselves about the source of that name, right? If we think about oxidation numbers, right? The oxidation number of zinc in zinc metal is 0. The oxidation number of zinc in the zinc ion is 2 plus. So our oxidation number is going up, right? So one way to recognize oxidation is that the oxidation number increases, in this case from 0 to plus 2. And then conversely, in reduction, the oxidation number decreases, right? So here we're going from 3 plus down to 0, okay? So we've got an oxidation process and a reduction process, and then the stoichiometry reflects that we have to keep the number of electrons balanced, right? The number of electrons transferred in each reaction is unbalanced. And as we showed when we were balancing oxidation reduction reactions, right, the number of electrons lost by one process has to equal the number of electrons gained by the other. So it's going to take 3 of this reaction to give us 6 electrons and 2 of this reaction to give us 6 electrons. Okay? So we're used to oxidation and reduction occurring when things are in contact with each other. Now we're going to look at a way to isolate those reactions so that we can quantitate the potential for these electrons to be transferred from here to here. Right, so here we have a setup for an electrochemical cell, right? A device that will let us separate those 2 reactions going on. That is, over here, zinc being oxidized and over here, iron being reduced, right? Those 2 reactions can go on in separate places, right? Now, a couple of things have to happen. One, we need a wire connecting the 2 through which our electrons will flow, right? So our electrons will be flowing in that direction, right? As we note here, they'll leave the zinc, they'll flow through this wire, they'll go into the iron, and they'll go to the edge of the iron electrode, and iron 3 ions will take up those electrons and become iron metal. So on the zinc electrode, zinc ions will be being formed out of the zinc as electrons leave. And in this electrode, iron will be being deposited on the surface as iron ions in solution take up those electrons to become iron metal. Okay? And we're starting with 1 molar of the ions in solution so that we're at standard conditions, right? And we're also working at 25 degrees Celsius. All right? So this lets us separate our two reactions. So as we said, the cell we have on the left is where oxidation is occurring, right? And so we call that the anode, if you make an E properly, right? The cell on the right is where reduction is occurring, and we call that the cathode. There are lots of mnemonic devices. The easiest one is the things that start with vowels go together, the things that start with consonants go together. Oxidation occurs at the anode, reduction occurs at the cathode. Okay? Now, we can set this up, right? And this reaction will go. In order for it to go, there must be a salt bridge to complete the connection, right? As zinc ions are forming here, nitrate ions can come out of the salt bridge to maintain charge balance. As positively charged iron ions are taken on, sodium ions can flow out of the salt bridge to keep the charge balance in the cathode, right? So ions are moving here to balance either the gain in ions in the anode or the loss of positive ions in the cathode. Okay? Now, the other thing we can do is that we can put a meter in our line of electron flow. And in this case, we've chosen a voltmeter, right? And so what are volts? Right? Volts are a measure of the potential energy associated with moving electrons. And volts are in units of joules per C, where C is, and that's capital C, coulombs of charge. Right? Coulomb is a unit that we use to measure charge. It ends up that there is a relationship called the Faraday relationship, usually written as a fancy F, right? So the Faraday relationship is that there are 96,485 coulombs of charge per mole of electrons, right? So we've got, volts are related to energy per amount of charge that's moving, right? And now we can relate that how much charge is moving to moles of electrons, okay? And it ends up, if we put that meter in there, this cell has a potential of plus 0.72 volts, right? And so a positive, right, a right, we call that the E, or in this case the E0, right, for this cell, right? Again, if E0 is positive, the reaction is spontaneous. If the E0 is negative, then the reaction is not spontaneous. And so clearly we're going to connect our cell potentials, E, with delta G at some time here in the future. Reactivity in oxidation reduction reactions is tabulated as standard reduction potentials. Now, what do we mean by standard, right? We need something to compare against. And our comparison is always this standard hydrogen electrode, right? And so in the standard hydrogen electrode, right, you've got hydrogen ions and hydrogen gas, right? If we've got this on the oxidation side, our reaction will look like this. Hydrogen gas being oxidized to 2 hydrogen ions plus 2 electrons, right? And so, since neither one of those is a solid that we can use as an electrode, we pick something like platinum as the electrode because it doesn't react really with either one under these conditions. And so we put 1 molar hydrogen ions in our solution, and then we have a tank of hydrogen gas, and we bubble hydrogen gas across the electrode at a standard 1 atmosphere pressure, right? And so if we put this electrode on both sides, we would get a potential of 0. But if we put this potential here on our oxidation side, and we put some other metal with its electrode and that metal in solution on the reduction side, then we can get a standard comparable voltage, right? And so we can do this for lots of metals. We call these standard reduction potentials because we've got the metal on the reduction side, right? And so, right, our electron flow is assumed to be in this direction. And so if we get a positive voltage, then our electrons are flowing in that direction. So things that give us positive voltages, right? So if we use gold, we get a potential of plus 1.50 volts. Or silver, we get plus 0.80 volts. Or platinum, we get plus 1.2 volts. Or copper, we get copper 2, we get plus 0.34 volts, right? So if we put any of those metals over here, electrons will flow this direction. We'll get a positive measure for our voltage of these numbers, as long as we have 1 molar of these ions in solution, and we use this metal, that metal, as the electrode. Now, not all metals are easily reduced by the standard hydrogen electrode. There are some other metals which, if we put them in there, we get different potentials. Like iron 3, we get negative 0.036 volts, right? So getting a negative voltage means that the flow isn't in the direction that we expected, right? It's not spontaneous that way, and so it will be spontaneous going this way. So for these, right, when we get down here, right, our metal is being oxidized, and our hydrogen is being reduced. Right? Because electron flow would be pushed back this direction. Right? We'd get a negative voltage. Okay, so some other metals that give us a negative voltage, right? Zinc, that we talked about, a negative 0.76 volts. Aluminum, a negative, right? Those aren't dashes, those are negative charges, negative signs, negative 1.676 volts. Okay? Now, in your book, both in the chapter and in the appendix, is a table of these standard reduction potentials. Right? And we can use these standard reduction potentials to predict whether oxidation reduction reactions are spontaneous. So we'll do that on the next slide. So here we're going to go back to our zinc iron system that we talked about originally. Right? We got zinc, we've got iron. Right? Here is the standard reduction reaction, right? Zinc being reduced to zinc metal, iron being reduced to iron metal, and here is that standard reduction potential that we just talked about, right? Now, at this stage, both of these potentials are negative, so neither of these reactions would be spontaneous, right, in the absence of other inputs. But we talked about using this, right? That this was used to protect iron using metallic zinc. Well, remember, right, we started with zinc being oxidized, so we have to write this in the reverse direction, zinc metal going to zinc ions plus 2 electrons. And if we do that, when we reverse the reaction, we reverse the sign, right? So the potential for that reaction is positive, is favorable. Now we go back, right? We keep our iron going the same direction, right? Because it has to be reduced. We have one oxidation, one reduction, right? That cell potential stays the same. Right? So we have our oxidation, we have our reduction, and that was just accidental that I wrote reduction in red. And to find the overall potential, right, you just add these two together, right, which would be 0.724 volts, which we wrote as 0.72 volts on that first slide, right, to two significant figures. Okay? So we can find the overall potential by just adding together the potentials after we figure out which one is being oxidized and which one is being reduced. Once we figure out what the oxidation is, we reverse that. And if we're trying to, here we knew we wanted this answer to be positive, right? We knew that that was a spontaneous process. And so, right, we can organize these to make sure that we get our positive answer, right? Whatever combination of oxidation and reduction gives us a positive answer is the thing that is the way we put these things together. Now note, at this stage, right, we don't worry about electron stoichiometry here. Right? That will come into the process later, right? So at this point, it's just the sum of the individual potentials give us the overall electrical potential. Okay? So we can use individual standard reduction potentials to figure out the overall potential for an oxidation reduction process. Okay? So we've got some other things to do. I think this video is getting long enough. I'll move on to some more quantitative considerations along with some other things in some upcoming discussions.